Good afternoon to everybody. First of all, I would like to thank all the people that last week in the first session, at the end, sent a thank you, which really I appreciate. I couldn't manage to do that through the chat, and I think I will not be able to do it today either. Now, on the second part of October 5, I discovered when I was presented, I discovered 3 misprints, 2 on page 36 and 1 on page 37, I think it was. And I just corrected them, and it was uploaded to the web. But because of the problems today, I think that you can download them from the following place. Just let me show you. This is one. Chat. Wait a second, everybody. Yes, you can download that second part from here. And the slides of today, you can download them from here. All right. Well, as you see today, because of the circumstances, I have to be presenting from home. And I hope that everything goes as well as if I were in the CRM. So the session today, the title is Reproducing Kernel Hilbert Spaces. Now, this actually is a session devoted to the reproducing kernel Hilbert Spaces, and particularly to their relation to algorithmic learning. Here you have a few references, but I will not go through them, except maybe number 3, a thorough treatise with a very extensive bibliography, which is Shortkoff and Smola, Learning with Kernels, Gilberto Machines, Regularization, Optimization Beyond. This is from MIT Press, 2002, and it's a very long book, as you can see. Then I also select this one, number 4, of Chauvet-Taylor and Cristianini, Kernel Methods for Pattern Analysis. But even if it says pattern analysis, actually this is part of algorithmic learning. It's a nice book. Number 6, I think this is Shalev-Schwartz and Ben David. We already met this book last week. Understanding Machine Learning from Theory to Algorithms. And it is a very good source for what I'm going to say. And finally, let me mention 9, which is, I already mentioned it also, Mori et al., Foundations of Machine Learning. Okay. There is a tutorial and survey, number 12, but to my taste is a little bit dense, and therefore I will not by now distinguish it. The index I'm going to follow is, I will first explain what are kernels, then I will explain some background on normed, Banach, and Hilbert spaces. Then I will go on to reproducing kernels Hilbert spaces. Then we enter the Kernel Studio to meet a few of the interesting kernels, and similarly, a very close notion, feature maps studio. And finally, we are going to work on learning with kernels. As the other day, there will be some break, but I will try that the break is not as long as half an hour, because most people said it was too much. So I may go a little bit over the hour, and then start a little bit before in the second part. So kernels. Well, it is clear that the word kernel has very many uses in mathematics and in the language. As for example, in mathematics, kernel of a linear map or of a group homomorphism, but in signal theory is more or less synonym of filter, and also in convolutional neural networks, and so on. Now, the kernels we are going to study here, or kernel functions, are quite different notions than the ones from mathematics or from filter theory. Although there is some kinship when one goes deeper into them. But they were actually introduced under the influence of David Hilbert, by James Mercer in the early years of the last century, and have a long, intricate and fascinating history. Actually, I take this from the Wikipedia. Here you have the link that James Mercer proved that. I'm going to read this because this is part of what we should have understood at the end of this lecture, of this session. That positive definite kernels can be expressed as a dot product in a high-dimensional space. And this is the basis of what is called the Kernel Trick. This trick allows linear algorithms to be easily converted into non-linear algorithms. Yes, I think it is not possible to understand everything for those that this matter is new, cannot be understood everything from now, but take into account this, that the space in which you are primarily interested is that curly X of the other day, maybe vectorial because you have represented it in this way, for example, in images or in audio, but it may be non-vectorial. It could be text, it could be strings of some sort, it could be graphs, many different sorts of structure. And in any case, then you can go to a high-dimensional inner product space, which is linear, but high-dimensional, work there, and by the kernel trick, be able to recover everything from the place you started with. Well, and in any case, the aim of this session is to unravel the main mathematical facts about kernels and their relation to algorithmic learning. So you may call them kernel methods. I stress these main mathematical facts because I think that once the mathematical facts are clear, then all the rest is also very clear, or much more clear. So let me see if I can take this out of here. Yes. I will start with a prelude on the versatility of the kernels. Can be defined on a variety of data, including vectors, text, and strings, among others. Can express powerful mappings, relations, and patterns, including classifiers, regressors, clusters, and rankings, among others. The algorithms based on kernels can deal with nonlinear phenomena in an efficient and relatively simple way. There is a comprehensive mathematical framework, the theory of reproducing kernel Hilbert spaces, that illuminates the data processing operations and the derived learning algorithms. And finally, there are convenient software packages that facilitate the computational aspects. More of that at the end of this talk, or of the session, or maybe tomorrow. So, still in the prelude, let's take some notions. Unless otherwise stated, all vector spaces will be real vector spaces. There are many things that can be modified easily to complex vector spaces, but it will not be my concern here today. Generic symbols for some families of vector spaces, I think is convenient. One is R to the n, is Euclidean space. As a matter of fact, this Euclidean space is a little bit more than a Euclidean space. It's a Euclidean space in which there is a distinguished orthonormal basis, which usually is called the standard basis. If you do not single out a special basis, then a more convenient notation would be En. I'm going to write this curly V for an inner product space. This is what it means, that is a vector space in that with a bilinear symmetric scalar product. This is denoted by x dot x prime, or by these angles x comma x prime. In any case, this is the inner product of the space. When the space will be a Hilbert space, I'm going to use preferably in general H, curly H, and if it's a Banach space, a curly V. And as we are going to explain a little bit these notions, just for being complete, and also in order that I have some material for my last session on November 9th, and so I can go a little further than what I could if I had to explain that again. Well, types of inner product spaces, I think this is very simple, but it's worth paying attention to it. If x dot x is positive for any x different from 0, then you say that the space is, or the quadratic form is positive definite. And as alias, I usually will say positive. If x dot x is greater or equal than 0 for all x, then it is said to be positive semi-definite. And in my parlance, semi-positive. If x, excuse me, this should be x dot x less than 0. If x not 0, this is negative definite, and negative in the other side. Please let me take a note of this so that I can correct it later. And finally, if there are vectors x for which x dot x is positive, and other vectors x prime for which x prime dot x prime is negative, then we say that the space is indefinite, or the quadratic form. A space curly V will be denoted by V sub plus if its inner product is semi-positive. Well, these types in the table correspond with same names to types of real symmetric matrices. These types can be defined in terms of the signs of the eigenvalues of the matrix. If they are positive or negative, the matrix is positive if all eigenvalues here are positive, and is negative if all eigenvalues are negative. Finally, it is semi-positive or semi-negative if they are bigger or equal than 0 or less than or equal than 0. And indefinite if there are eigenvalues of both sides. So let's go into the kernel functions. Here starts a little bit the main thrust of the talk today. So let X be a set. As I mentioned before, it could be vectorial in the sense that it could be inside some Rn or not. But this is not of no concern for the moment, at least. So a kernel, in the sense of Mercer on X, is a function that I will denote by kappa from X cross X to R, such that kappa of X prime is kappa of X prime X. So therefore, kappa is symmetric for all X prime in X. And with the property that for any elements in X, any points in X, X upper 1, X upper M, let's say, for any M, and any real numbers, lambda 1, lambda M, the following inequality holds. This is that can be called Mercer condition. This is that the sum with respect to I and j of lambda I, lambda j, kappa of xi, xj is greater or equal than 0. Here the point is that should be for any values of the lambdas and for any r, for any m. So you can choose any number of them. Well, what is clear is that this condition 1 means that the matrix formed by kappa of xy, xj for all I and j in the range of m, that this matrix, which is called the kernel matrix, or also by the form it has, a gram matrix of x1, xm, well, it is equivalent to say that this matrix is semi-positive, which in turn, as I said before, is equivalent to say that its eigenvalues are non-negative. By what we will see, especially in the examples, how do you have an intuition about kappa of x prime? Well, you can think about it as some kind of measure of similarity degree between x and x prime. And sometimes it could also be some distance between x and I, or it would be big if the kappa is big and a small distance if it was small. But the similarity goes the other way around. Well, there is two very simple facts that should be stressed. If kappa is a kernel on X, then kappa of XX for any vector is non-negative. Well, this is the case m equals 1 in the Mercer condition. On the other hand, if you have two vectors, x and x prime, then the kappa of x prime squared is less than or equal kappa of xx times kappa of x prime x prime. Notice that this implies that if kappa of xx is 0, this is 0, then this is 0, this square is 0, therefore kappa of xx prime is 0 for all x prime. So in general, it will not be a good data to have kappa of xx equals 0, because then it counts nothing with respect to all the others. Well, the proof of this fact is very simple. You take the kernel matrix for two vectors, x and x prime. This kernel matrix has this form, kappa of xx, kappa of xx prime, kappa of x prime x, kappa of x prime x prime. And this is, by the remark before, is semi-positive. And if it's semi-positive, its determinant must be greater or equal than 0. And this is precisely what we stated up here. Well, before proceeding, I think that it is worth having some outlook of where we are going to. Is this a little scheme in which you start with your curly X, the space in which you are interested to work. There you have a kernel in some way, you are interested in, let's say, a similarity relation, and then you cook up a kernel, let's call it kappa as before, and then you have some data, x1, xm. This kernel and this data gives rise to the kernel matrix that we just introduced. Now, finally, the learning algorithms of this part take the kernel matrix and produce a predictor of what should be a value for data x, points x in your space x, curly x, what should be the value of for that x. Of course, it is assumed that if it's in supervised learning, the value of the x upper I is known, but not for other data. Now, the predictor that the kernel theory gives is that the function a of x is a linear combination for some lambdas of these partial functions. So for the data x upper I, you consider the function of x kappa of xi x. This is a genuine function of x over curly x, over the set of data. And then you work smartly and you find some combination of these functions, and this will be the best predictor that the theory can provide. Again, this will be something that we are going to work in detail during the session. Let's give some examples. Some are easy, some are a little bit more involved. Those that are more involved, we are going to prove that they are kernels later on. So the simplest one is if you take an inner product space, which is semi-positive, curly B plus, is this one here. Then, if you define kappa of x prime as the inner product, this is a kernel. Now the space is B vectorial or BDB. Well, this we will say that this is the linear kernel or bilinear kernel or quadratic kernel on B. It depends on your taste about which terminology to use. Well, this fact, the fact that this is a kernel, which is to check that the sum 1 is non-negative, is very easy. Because if you take that sum for all I and all j, but now the kappa is already this inner product, then this, because of the bilinearity of the inner product, it can be rearranged as a sum of lambda I x upper I, which is here, and lambda j x upper j, which is here. But notice that this sum and this sum are the same vector. The only thing that changes is that here the index of summation is I, and here is j. So this is definitely greater or equal than 0. Let's go to the second example, which is, I call it the pullback of a kernel. Suppose that you have a kernel on some y, and that you have a map from x to y, and then you can define a function, kappa sub phi, on x cross x, with values in real values, by this formula. You take kappa of phi x prime, and you look at that as a function of x prime. And this function, you give a name, kappa sub phi. Well, this is a kernel on x, it's very elementary. A useful special case of this pullback is when y is a semi-positive inner product space, with k, the bilinear kernel. In this case, the kappa sub phi will be the inner product of phi x prime, whatever it be. Well, as hinted in the first session, particularly when curly v is r to the n some power, this v is usually called a feature space for x, for curly x. Phi is a feature map, and then kappa sub phi will be called the associated kernel. Now, kernels derived from other kernels. Suppose you have a family of kernels, kappa sub I on X, where I is any natural number. You may assume that it's bigger or equal than 1 or bigger or equal than 0. It doesn't matter. Let's suppose it's bigger or equal than 1. Suppose that this is a sequence of kernels on X, and that lambda I is a sequence of non-negative numbers. Well, then the following are kernels on X. 1, take exponents E1, ER, are exponents, NER, in N, and do this monomial in the kernels, kappa 1 raised to E1, kappa R raised to ER. Well, this makes sense as functions on X cross X. Well, it is easy to check that by induction, it would be enough to show that this is a kernel. It would be enough to prove that the product of two kernels is a kernel. We will see this approved later on, actually on page 30. Another one, suppose that the lim, when I goes to infinity of kappa I, exists. Well, this means that for any x and x prime in X, the lim, when I goes to infinity of kappa I of x prime exists, and this is the value of the limit at x and x prime. This is very easy to check because this limit, when you do the matrix, the kernel matrix, for each kappa I is semi-positive, and then when you do you check the kernel condition, it is reduced to the kernel conditions of the kappa I and the fact that the lambda I are positive. Well, a special case of this number 2 is is that if you have a series sigma for I greater or equal than 1 of lambda I kappa I, if the series converges, again, for any x prime in curly X, then the sum of this series is a kernel. In particular, a linear combination, of course, I didn't say this. Yes, I said this, lambda I are positive, are non-negative. In particular, for lambda 1, lambda R non-negative, this linear combination is also a kernel. A special case of this number 3 is the exponential of a kernel. Well, this exponential, the coefficients are non-negative. Actually, they are positive. And the kappa in the exponential is kappa j. So this, by this case, is a kernel for any cap. This converges for any k. More generally, you could take a power series, A of t. Well, now I sum from 0 to infinity, aj, tj, power series in one variable, and you take a sequence of non-negative coefficients, A0, aj, the coefficients are non-negative, then you can define a kernel on X if we assume, then we can substitute in T the kernel and obtain a kernel that can be denoted by A of k. And this will work if the kappa of x prime is in the range between minus r and r, where r is the conversion radius, or the radius of convergence of A of t. This is the special case of the series. This is less obvious, but and we will work on it later. If kappa is a kernel on X, then there is what is called the normalization of kappa, kappa bar of x prime, which is defined as follows. If kappa of x is 0 or kappa of x prime is 0, then it is defined as 0. Otherwise, if this is non-zero and this is non-zero, then you can take a denominator with the square roots and the kappa in the numerator, and this is the normalized kernel. We will see a proof of this later, and in fact, on page 31. Now let's look at some concrete examples. The following are kernels on the specified curly X. Well, the one which is nobody tells it's a kernel, but it is a kernel. For if you set kappa of x prime equals a positive constant, sorry, a non-negative constant, then this is clearly a kernel, and it can be called a constant kernel. Polynomial kernels. If X is an inner product space, a semi-positive inner product space, in particular if V is Euclidean space, then for any constant A, non-negative, and any exponent D, kappa of x prime equals to A plus x dot x prime raised to the D, this is a kernel. The integer D is the degree of the kernel, and it should be noted that if you fix one of the variables, say x, then kappa of x prime is a polynomial of degree D in x prime, because if x is frozen, then this is a linear polynomial, and raised to D is a polynomial of degree D. Another example, 3, if curly x's are n, and you take alpha positive, I denote with plus plus that is positive, not so a little stronger than non-negative, and D is a natural exponent, then the function kappa of alpha D of x prime, which is equal to the exponent of minus alpha x minus x prime norm to the D, the norm in Rn, this is a kernel. Well, the case D equals 1 of this expression is called the Laplacian kernel. And the case D equals 2, the Gaussian kernel. In this case, alpha is expressed usually in the form 1 divided by 2 sigma square, just to make sigma have the dimensions of the norm of x minus x prime. That this is a kernel will be seen later on page 32. It's not completely obvious that it's a kernel. And in principle, how would you check the Mercer condition? It's not clear, but it will be very clear later. These kind of functions, for example, the Gaussian, have what is called the radial property. What does it mean? This means that if you fix x, for example, and look at this as a function of x prime, then this function of x prime decreases radially around any given x, in the sense that it depends only on the norm, separating x prime from x, and therefore decreases radially around if you took x as a set. By the way, these functions in the literature are usually called radial basis functions, RBF. Since I'm not going to use this terminology, I have not included it here. I think that just explaining that they have a radial property, it's more than enough. Let's go now to what we said, the background on normed Banach and Hilbert spaces. Most of you will know about that, but it will not take long to have a little survey. And this should be also to fix notation and to clarify some concepts. And I insist on what I said at the beginning, that this will is the last session of mine, which is on 9 November. Again, I will only consider real vector spaces, and everything can be adapted easily to complex vector spaces. Well, you have to take that into account, the conjugation in C, but if you know the real case, the complex case is much easier. Main references I take because there are things that I'm not going to prove. 13 is J.V. Conway. This is not the Conway that died of COVID. It's an analyst. A course in functional analysis, second edition. volume 95 of Graduate Text in Mathematics. And 14, the book of Royden and Fitzpatrick. It's an excellent book on real analysis. The one I have is for the fourth edition. It was published by Prentice Hall in 2010. Here there are very clear explanations of all the concepts and very clear proofs of everything that is needed. So, norm to spaces. A norm on a real vector space L is a function that you denote in this way, from L to R, having the following properties. First of all, the positivity property, which means that the norm of X is always non-negative for all X in L, with equality even only if X is 0. The second property is homogeneity, and it means that the norm of lambda X is the absolute value of lambda times norm of X for all X in L and lambda in the real numbers. And finally, the third one, the triangle inequality, is that the norm of a sum is less than or equal the norm of X plus the norm of X prime. Well, the pair formed by a real vector space L and the norm is called a norm vector space. For example, the Euclidean linear spaces, Rn, for example, the norm is the square root of the sum of the squares. A less obvious example, at least for the people that have not seen it before, is little l upper p, where p is any value, any natural value from 1 to infinity. What is this? This is the space of real sequences. Let me denote it by elements by x, and the terms of the sequence by xk, k bigger or equal than 1, such that this expression, you do the sum for k from 1 to infinity of the absolute value of xk raised to the p, and then of all this sum, you take the root 1 divided by p, or you take the pth root of this. Now, the sequences for which this expression is less than infinity, these form the space little p, and its norm is defined by this expression. For the case infinity, it goes a little different. Little l infinity is the space of absolutely bounded sequences x with the norm, norm sub infinity of x is the supremum of the absolute values of the terms of the sequences. Absolute value of xk for all k. So at least we have these examples. Now for the Banach spaces, in a norm to space, the notions of convergent and Cauchy sequences make sense. A sequence, let's review this a little bit. A sequence x1, x2, xn in L is convergent if there exists a vector b, such that the norm of the difference, xn minus b, goes to 0 as n goes to infinity. If this is the case, v is unique, and then you write that b is the lim of this xn. On the other hand, a sequence xn is said to be a Cauchy sequence if for any epsilon, positive epsilon, there is a natural number n, which will depend on epsilon, such that the norm of the difference xi minus xj is less than or equal epsilon for all I and j beyond 10. Well, any convergent sequence is clearly a Cauchy sequence. Well, it can be seen easily that is a Cauchy sequence. Now, the norm to space B equals L with the norm is said to be complete, or a Banach space, if any Cauchy sequence is convergent. Examples, the space is little l upper p for any p between 1 and infinity are Banach spaces. Another example is that if you have X a compact topological space, then if you can think of it as a closed bounded set in Rn, then the space of continuous function on X, which I denote in this way, with the supreme norm of f, the supremum of the values of X for any X in X, this is also Banach space. the Banach space of continuous functions on a compact space. Well, a key point is that any normed space, L with a norm, can be enlarged to a Banach space. Well, this process should be familiar if you remember the construction of the real numbers as a completion of the rational numbers. In fact, the absolute value, this, is a norm on Q, I don't know, R, and R can be defined, at least I think this is a very easy, from the point of view of algebra, this is a very smart definition, as the quotient of the ring of Cauchy sequences in Q by the ideal of null sequences, which are sequences that are convergent to zero. So convergent sequences amount to nothing in terms of producing real numbers, but all the others do produce a real number, well, except the zero. But similarly, we can form the quotient L bar, we have this space L bar of the vector space of all Cauchy sequences in L, which is clearly a vector space, by the vector subspace of all null sequences. We know that L is contained in L bar by mapping an x in L to the class of constant sequences, xn equals x for all n, and that the norm on L extends to a norm on L bar by setting norm of x bar, for x bar in L bar, as the lim, when n goes to infinity, of the norm of xn for any Cauchy sequence representing x bar, Cauchy sequence xn. This works, and the details are in the books. Another example is the Lebesgue space is L upper P, L of Lebesgue. For details, see again 14, chapter 7. Well, if this may, for some people it may be a little bit, it may be unknown, but for other people it may be trivial. So in any case, I'll explain it. Let X, curly X, be a space X, a subset of X called sigma with some properties, and a function mu from sigma to the real numbers, to the non-negative real numbers. And this is called the measure space if it satisfies some axioms. And it's defined for all P, for all natural P from 1 to, well, for all natural P beyond 1. Well, for any measurable function on X, one can define a norm sub P by taking, it's very similar to what we said by little p. You take the norm, the absolute value of f, you raise it to the p, you take the integral with respect to this measure, this is the Lebesgue integral, and you take the pth root of this, and this turns out to be, we define this in this form, sorry, okay? Now, the Lebesgue space, or simply LP of mu, is the set of all measurable functions from X to R, such that this expression that we call norm of F sub P is less than infinity. With, let's do this abuse of notation, with the convention that two functions are equal, even only if they agree almost everywhere. So they agree in all X, except maybe on a set of zero measure. The space LP is a normed space with that norm sub P. This is a consequence of what is called the Minkowski inequality. And in fact, it is complete. This is the famous Riesz-Fisher theorem. And hence it's a Banach space. This is why it's an example of Banach space, okay? By the way, the space little l upper P is the special case when X is the natural numbers with a counting measure. Well, this, I think this, I will reserve this for November 9 because it's a little bit technical and it will play the main role there. So let's leave it here now. The Hilbert space, the concept is a natural extension of the notion of Euclidean space to possibly infinite dimensions. So let H be a real vector space endowed with an inner scalar product, as before, for all x, y, that is linear, symmetric, and positive definite. Positive definite. So x, inner product of x and x is positive for all x different from 0. In some context, and maybe myself later on, this is denoted also by x dot y. The norm, H is a normal space by defining the norm as the plus square root of the inner product of x with x. This makes sense because this is a positive or zero number. In this case, the triangle inequality has the property, an additional property, that it is an equality even only if either x is 0 or x prime is a positive multiple, scalar multiple of x. This actually is a consequence of the way you prove this for this positive space. It is, if this normed space is complete, then we say that H is a Hilbert space. Obviously, any Hilbert space is a Banach space, and for example, the L2, the Lebesgue L2, turns out to be a Hilbert space with the inner product defined again by a Lebesgue integral of x, fx, gx with respect to measure mu. This, in the complex case, there should be here a conjugate for g. And the same for L little l upper 2, in which the inner product of two sequences is defined. You take the product term by term and we use sum. This is well defined for L2, and so it defines an inner product. There is a little lemma of the Hilbert space that I will be using, which is the following. If H is a finite dimensional subspace of a Hilbert space, curly H, then H, it decomposes as the direct sum of H, sum the perpendicular of H, the perp of H, which by definition are all H prime in H, such that H, the inner product of H and H prime is 0 for all H in H. This is the current definition. Well, this actually what I'm going to prove is also true if H is a closed subspace. A condition that for a finite one is not needed because automatically it is closed. So how do you prove this? I think that you can follow the argument in these graphics. Well, this is a fact. I'm not going to prove this, but what I'm going to need is this. For any H in H, there is a unique decomposition into one element x hat of H and an element H prime from curly H perp. Now, since the inner product of H hat and H prime is 0, it turns out that H, inner product of H and H, is the inner product of H hat and H hat plus the inner product of H prime, H prime. Well, this is a form of Pythagoras theorem, and therefore the norm of a square of H is the normal square of H hat plus the normal square of H prime, okay? I will need it a little later. So let's go now to reproducing kernel Hilbert spaces. This probably should be or could be more novel for some people. What I explained so far is not had very little novelty. Definition. If kappa is a kernel on X, so a function that X cross X to R, and X is an element of the space X, we will write kappa sub X from X to R. I already hinted to this function at the beginning, to denote the function defined with this formula. Kappa sub X of X prime is kappa of x prime. Okay. Now, suppose that you have a Hilbert space curly H, whose elements are functions from x to the real numbers. If you have that, then you say that kappa is a reproducing kernel for curly H if this function kappa sub x belongs to the Hilbert space for any x in x, and this is the fundamental relation. The value of f at x is expressed by this inner product of kappa x with f. This should occur for all f in curly H and for all x in x. This is the reproducing property to which alludes the reproducing kernel property in the name of those spaces. Well, in particular, we have this. Kappa of x prime, by symmetry, is kappa of x prime of x. This is kappa sub x prime applied to x. But then you take for kappa x prime like this f, and it turns out that this will be the inner product of kappa x prime. So it means that under these circumstances, the kernel can be defined by an inner product in the Hilbert space. This is defined in X. This is defined in the reproducing kernel Hilbert space. Well, this means, with the terminology used before, that we can regard curly H as a feature space. We can regard the map phi of x to h that sends x to kappa x as a feature map, and by this relation, kappa is the kernel associated to phi. Kappa is the kappa sub phi in the sense of the pullback I said before. We will often write phi of x instead of kappa of x, particularly when this helps in the readability of the expressions that we are going to encounter. A little remark, the condition f of x equals kappa of x inner product f implies that the evaluation map from H to R for any point x, the evaluation map sends f to f of x, is continuous for any given value, for any given point x, because this is certainly continuous, if you fix x, continuous in f. Let me explain now the scalar product in terms of the kernel. By this I mean the following. Suppose you have a finite number of points in curly x and the scalars lambda 1, lambda m. Then we can consider the function, a finite linear combination of the phi of xi, or kappa sub x sub I. Linear combination, this is clear, this lies in H. Then if you take f prime, another function of the same form, so another combination for other data, then the inner product of f and f prime is equal to this expression. This is clear by the fact that that phi of xi, phi of x prime j, is the kappa of xi, x prime j. So you have this. If f is as above and f prime, you specialize f prime to a kappa of x, which is phi of x, then what you obtain by doing the calculation is that phi of x inner product with f is f of x. This ratifies the reproducing property for these particular functions, f in curly H. Well, the such space of curly H spanned by the functions phi of x, which are kappa of x, will be denoted if it is needed as curly H sub 0. It is to note that H sub 0 and its inner product, the one we defined here, only depends on the kernel, because this expression only depends on the kernel. Well, and of course, the functions themselves. Now, let's just sketch the existence theorem of the reproducing kernel Hilbert space. So let kappa be a kernel on X. Then there exists a Hilbert space curly H, and the mapping from curly X to curly H, such that kappa of X prime is phi of X prime for all X and X prime in curly X. Okay. Well, the proof is hinted by what I said in the last slide. Let Vk be the vector space of functions from X to R spanned by the functions phi of X. The elements of Vk are finite linear combinations of the form, as said before, a finite set. You take the combination, and if you take any two of these, H prime, so another finite linear combination, then you define an inner product in Vk, B kappa, by this formula. This expression only depends on H and H prime and not on the linear combinations used to represent these functions. For example, the calculation already done, the right-hand side of star is equal to this. You take first the sum with respect to X, then with respect to X prime, and it turns out that this is this function applied to X, which shows that this function applied to X, which is the H prime. So this shows that it only depends on H prime, not the representation. And similarly for the function X, for the function H. The reproducing property for Vk, we already saw it. Phi of X inner product X prime, the one we have just defined, is H prime of X. The semi-positivity is the same argument we used before, or similar argument. You take M points on X, you take H, this expression, and then H inner product H has this expression, which by the definition of the Mercer kernel is greater or equal than 0. So clearly it is semi-positive. Now, this Vk will not be complete, but you can complete it as I explained before. So let H be the completion of this V kappa. This is already Hilbert space, and this is the reproducing kernel Hilbert space associated to kappa. How do you do that? Well, in general, is the same philosophy. For any X in curly X, the evaluation map of Vk in R is continuous. We already saw that. You can appeal, as you could have appealed before, to the Cauchy-Schwarz inequality. So kappa X of H is well defined for any, by taking limits, for any H in the completion. And the reproducing kernel extends to from Vk to H by just a limit argument. And as I said, this curly H that we just constructed, or at least outlined how to construct it, is the RKHS space associated to kappa. Well, let me go a little bit over the time as I explained. Well, I don't know if I explained to everybody of you, because there are more people now. So I think I will go half an hour. It was judged to be too much. So I will explain a little bit more. Then there will be a shorter break, and then the second part. Kernel Studio. So let's go into the studio to take some pictures of these kernels. And first we are going to consider the product kernel, the product of kernels, then the kernel normalization, and finally the Gaussian kernels. The product of kernels, we want to prove that the product of two kernels is a kernel. I already mentioned that if this is the case, then any monomial in kernels is a kernel. Well, let capital K and capital K prime be the kernel matrices of kappa and kappa prime relative to the same set of M points of curly X. Then the kernel matrix of kappa kappa prime relative to the same endpoints is this. It depends on ij, so it's an m times m matrix, and since it's a product, it's kappa ij times it's k ij, k prime ij. Is this product for the same ij? Now, to prove that kappa kappa prime is a kernel, we have to check the Mercer condition, that this sum for any lambdas with respect to I and j of this expression, kij, k prime ij, is non-negative. Well, for this, we will use that a semi-positive matrix kappa k can be expressed in the form, the product of m times m transpose for some m times m matrix. This is the Cholesky decomposition. If it's not fresh in your minds, you can look, for example, at this book, which is, actually this book has many, many interesting things. It was published a couple of years ago, of Gilberto Space, Linear Algebra and Learning from Data. This is an MIT professor. So you take this Cholesky decomposition, and then you have the following. The argument is here in these red formulas. So you decompose this sum, same sign with lambda I, lambda j, but now you express the kij and the k prime ij in terms of the m, okay? Well, since on the right-hand side is transpose, you are going to have mik, mjk. Okay, if it was not transposed, it would be the other way around. So you have this times k prime ij. Now you first sum with respect to k, from k to 1, from 1 to m, and then this is with respect to the data points, and then sum from with respect to I and j. You can take the lambda I with this lambda I mik, the k is taken care of here in the beginning, and the lambda j with mjk, which is here. And what do you observe here? You observe that this is a lambda prime, lambda I prime. This is a lambda j prime. This is a kernel. Therefore, each of these expressions is non-negative, and therefore their sum is non-negative. Okay? So this ends the proof that the product of two kernels is a kernel. Let's go now to the kernel normalization. Given again data points x upper 1, x upper m in kernel x, let us check that the matrix k bar is the matrix of the normalized kernel of xi, xj is semi-positive. Well, what do we have to do? Well, for any lambda 1, lambda m, we need to prove Mercer's inequality. Good. Now, if kappa xi were 0, then by a remark I made some time ago already in a former slide, this would imply that kappa bar of xi, xj is 0 for all j. This is by the definition of kappa bar. So it does no harm to assume that kappa xi is different from 0 for all j. Okay, so if this is the case, and we said hi equals kappa x upper I to use the notation, that this kappa bar xi xj is the inner product of xi xj aj divided by the square roots of the kappas, which is the norm of hi, norm of hij. Now the scalar product and the norms are relative to reproducing kernel Hilbert space associated to kappa. And now the value, this value, now this value here is just this, and this, by an argument similar to other ones, is just the inner product of this vector times this vector, which are the same, because the only thing that changes is the summation index. So indeed, the normalized kernel is a kernel. Finally, in this Kernel Studio, we have the Gaussian kernels, and the proof that the Gaussian kernel is a kernel is that its expression, which is this, actually is the normalization kappa bar of this kernel. What are we saying here? Well, x dot x prime is surely a kernel. Is the bilinear kernel in the Euclidean space. Divided by a constant, it is still a kernel. You can take the exponential, and by what I said before, this is a kernel. So clearly you can define this. Now, if you have this kernel, you can normalize it. What do you get if you normalize it? Well, the kappa of xx is this, clearly, because if x prime is x, this is the norm of x squared. Similarly, the kappa of x prime is this, and therefore the normalization is the kappa of xx prime, which is this, sorry, the kappa of x prime, which is this here, the kappa of xx, which is this, and the kappa of x prime, which is this. You do your arithmetic, and you clearly get this, because you have, here there is a 2, here there is no 2, so actually here you get a 2, a minus and a minus, because they are dividing, and you get this. So this is wonderful to have that the Gaussian kernel is indeed a kernel in the sense of today. I think now I'll take a break of about 15 minutes. So I will resume this at 5:25. Okay? Now, since I'm in this under the circumstances today, let me see if there is some new. Well, here, Julia Chardy says, can we have the recordings, please? Well, these recordings, as far as I could see, a link was sent to the whole list for the recordings of the first session. And the recordings of the session today is being done, and they will be posted or sent to you, the link, maybe tomorrow, I hope. Now, what else?
I have a question, Professor.
Yes? Can you say your name?
Yes,
oh, okay.
I'm Victor.
Victor.
I suppose you could prove also that the Gaussian kernel is a kernel by proving the three properties, no, that have this kernel. The positivity, the homogeneity, and so on.
Well, the kernel, the norm has these conditions. Well, maybe, yes, you could do it. As in several cases, there are different ways of doing something. I just wanted to illustrate the normalization case. Okay? Does it answer your question?
Yeah, sure. Okay. I was just curious whether you could prove it by just checking the Mercer condition. I think is the one. If it is an alternative option to check this,
Well, I have seen at least a couple of proofs in addition to the one I made, but I explained this, that I thought that it was a good example of the normalization kernel. Okay, and okay, thank you. Then, somebody said here Neil Rodellas Gracia, that the slides of the video of the first session is here, so it's for everybody. And Julia says thanks a lot. Yes, I guess they will be put tomorrow. That's fine. So let me take this break of about 15 minutes, and then we continue. So let's continue this journey. We'll get into the feature maps studio and meet polynomial feature maps, feature map of the polynomial kernel, and the feature map of the Gaussian kernel. So polynomial feature maps. I need some notation. Let curly J be the set of length n sequences of non-negative integers. So J is J1, Jn, with, and we were going to set absolute value of J, the sum of the J's. Now, if J is one of these sequences, and X is an element in a vector in Rn, having components x1, x2, xn, then I will denote by X upper capital J this monomial. This is a monomial of degree, this J between bars. I don't know how to call it, okay? I'll say absolute value of J. Let capital N be the dimension of the space of polynomials of degree D in n variables. We are going to calculate it in a moment. Then we have a feature map from R little n to R capital N, such that the jth coordinate of phi of x, the coordinates in this space, are going to be labeled by the j's, by the sequences. The coordinate of phi of the jth coordinate of phi of x is x to the j. Well, a degree D polynomial map defined in Rn can be written in the form a sum from from 0 to the degree of the homogeneous part of degree R for any R. So it will be a coefficient Wj affecting X upper j. Formally, this is W dot product phi of X. It can be explained this form, okay? Well, where W in R upper n is the vector whose components are the coefficients of the polynomial. By imposing further restrictions on the J, on the sequences, used in the definition of the polynomial P of X, we can get polynomial feature spaces of lower dimension. For example, if we only sum with respect to sequences of absolute value the degree D, then this is a homogeneous polynomial of degree D. And the dimension of these polynomials is D plus n minus 1 over D, this combinatorial number. Then the dimension of the polynomials is counting, adding up all the homogeneous parts of the polynomials from D minus 1, all the way to D equals 0. By the way, if there are algebraic geometers among the audience, this feature map given by the polynomials is called Veronese mapping. It's a very old geometric mapping studied ever since the 19th century. Now, let's turn to what is the feature map of the polynomial kernel. Remember that the polynomial kernel was a power D of an expression that had a constant plus the inner product or the dot product of x times x prime, okay? Well, here it is, kappa of x prime is 1 plus x dot x prime to the D. I put the constant equals to 1, this is irrelevant because otherwise you could divide by, take out the constant in some way. So we know that there is a feature map by the theory that I explained. There must be a feature map from Rn to some h, such that the kappa of x prime is the inner product of phi of x prime. So what is this phi? Well, to find an explicit expression for h and phi, we define for any x in Rn and any sequence J1, JD. Now it's a sequence of d terms, and these terms can be from 0 to n. It's a little different from what I explained in the previous slide. Well, having that, you define x lower j as xj1 times up to xjd. So you multiply only these coordinates of the vector x. The coordinates indicated by j. We make a convention, though, that since the indices may be 0, then we take the x0 to be 1. It's an extension like when you do projective geometry, for example. Then we can consider the vector in the space R raised to n plus 1 to the d, phi of x, whose coordinates are the monomials xj. Why do I put this funny number here? Well, because this is the dimension of these sequences, okay? It's the number of these sequences, y per tant is the dimension of the space. The claim is that kappa of x prime is phi of x inner product phi of x prime. So with this, we have found out the feature map of the polynomial kernel. Well, the proof is simple. Phi of x, sorry, this is wrong. It should be here. Okay. Slide 35. Okay, sorry for that. If I do not take a note, I forget. So phi of x, inner product phi of x prime, by definition in an Euclidean space, is the sum of xj, x prime j, for all j. Now look at this. You can regroup this by taking the j1 with the j1, the j1 of x with the j1 of x prime, and so on up to the jd of x to the jd of x prime. This is this expression. Now, on the other hand, the kappa of x prime is, sorry, here it should be an x prime again. Kappa of x prime is 1 plus x dot x prime to the d. This here, with the convention that the x0 is 1, can be written as x0, x0 prime, x1, x1 prime, which is this, xn times xn prime. And when you do this, you develop this power d, clearly you get this expression here because of the properties of multiplying polynomials. So with this we have checked what is the feature map of the polynomial kernel. Finally, the Gaussian kernel is a little bit more complicated because we need a space of infinite dimensions. Actually, at the end, we need the little l upper 2. So we start with the Gaussian kernel. Here it is. We use similar notations as before. So phi x sub j now will be this. Well, there is this part which comes from one by analogy to this expression. And then I have the xj as defined before. And you need, since you have a sigma, to divide here by x sigma k. This is the case sum n, so you have this. And now the j's belong to one n, but otherwise there can be any number because k is any number. Well, let S be the space, curly S be the space of real sequences indexed by the j in some order. Then we have a map from Rn to this space X given by this formula. So phi of X has the coordinate j is given by this expression. And the claim is that for any xx prime in Rn, the kappa of xx prime is this sum, which is the dot product in the space S of phi of x with phi of x prime. Well, indeed, this again is a little algebra. The sum on the right-hand side can be expressed by using this. You just take what is phi of x, phi x sub j, phi x prime sub j. You take these expressions, and you get this times this sum. But this sum here, by the same argument as before, is this thing, is x dot x prime raised to the k. And therefore, the whole sum, this sum here is the sum for any k of this expression times the sum for absolute value of j equals k of xj prime, and this turns out to be this exponential. And finally, maybe this is something related to the question of Campello before, Campello or Campello? Campello, I suppose.
Campello, yes.
See, okay, thank you. So you get finally the kernel, okay? Now the proof shows, if you look at this carefully, the proof shows that phi of x actually is in little l squared. So that actually the feature space is little l squared, this subspace of S. Well, this ends the feature studio, the feature visit. Now, the main, probably from the point of view of algorithmic learning, this should be the main part, learning with kernels. But I couldn't see a way of doing this without refreshing or reminding all the things I have been saying so far. So learning with kernels, there will be a basic scheme which will reproduce that graphics at the beginning. We are going to prove the Representative Theorem. We are going to explain in detail what is the kernel trick. And then we are going to apply this kernel trick to the kernel support vector machines, both hard, which I already explained last week, and soft, which I will explain today. So the basic scheme to approach a learning task on our space X, curly X, by means of a kernel K, kappa, can be described as follows. First, you choose a feature map, a feature space, curly H, and the feature map phi from X to H. Then you morph the label data set you should be working on in curly X, namely X upper 1, Y upper 1. It's a labeled data set, okay? X upper 1, A upper 1, Y upper 1, up to X upper M, Y upper M. And this morphed data set is, let me call it D bar. Instead of X1, you take phi of X1, and so on. Instead of XM, phi of XM. So this is a data set in the feature space, a labeled data set in the feature space. Now, this data set can be trained and do like in the support vector machine that we explained last in the first session. You can train a linear predictor H bar from H to Y, where Y is the space or the set where the labels belong. Let's suppose it's real numbers or in regression, or could be a finite set if it was if it was classification, okay? And now return, you do somehow the pullback of this H bar, return the predictors H hat from X to Y, such that H hat of X is H bar of phi of X. Well, a very simple example, which is a special case, a very special case of the polynomial feature map, is this thing. Suppose you have a polynomial, variable, P of t of degree d, and a labeled data set, which is m values of the t and the values of the polynomial. Let's take as H the Euclidean space R of dimension d plus d1, and take as phi of t this vector of length d plus 1 t up to TeV. Well, learning P of t in the original R is morphed into learning the linear map from H to R, let's say W dot X, with W the coefficients of your polynomial, from the data set, the morphed data set, phi of T1, phi of Tm with values P1, P1. This is very clear. So it means that you can do polynomial regression, let's say, by doing linear regression in a space of higher dimension d plus 1. And there would be similar things for the case of the polynomial feature map. Now, the beauty of all this is that phi may be highly nonlinear, like, for example, the Veronese mapping, the polynomial feature map. So this can be very nonlinear. H bar will usually be linear. We train linear predictors. So the composition will be highly nonlinear in the original space curly X, okay? So this means that at the end of these steps, you are going to get not separating hyperplanes of your data, but a high degree or complicated hypersurface that is going to be separating one class from the other. And therefore, it means that in somehow you can manage nonlinear problems of classification, for example, by knowing how to do the linear case. We will see a little later how this goes in the case of the support vector machines. Now, the representative theorem is a theorem that I think it's, for me, I feel that I have to prove it, explain and prove it, but I will not use it up until the very end, explaining that something that I will do in a different way can be done with this theorem. But this theorem is important, so should be proved, should be stated and proved here. So let kappa be, and you are going to see why it is called the representative theorem, as in here, okay? Let kappa be a kernel on X, H the corresponding reproducing kernel, Gilberto Space. Let's take some data, x1, xm, in X, and set to simplify notation, as before, hi equals phi of xi equals kappa xi. And define the finite dimensional linear space spanned by these h1, hm. Good. Suppose that sigma from R to R is a non-decreasing function, and that L, in principle, can be from Rm, m is the same as the number of data points, to R disjoint union with infinity. So we allow that at some places it could be infinity. But otherwise, it's an arbitrary function. Arbitrary function, I stress that. Then the optimization problem, which is finding the mean for H in H of L bar of H, where L bar of H is defined as sigma of the norm of H plus L, the L we have here, of Hx upper 1, Hx upper m. This minimization problem, this optimization problem, admits a solution of the form H hat a linear combination of the HI. I stress this, a linear combination of the HI. This in the context or with the notations of that little diagram I showed early on is the bottom at the right, at the right bottom, at the bottom on the right, the final linear combination, which is the predictor given by this kind of thing. Okay, moreover, if sigma is increasing, then any solution of problem number 2 has this form. Okay? Well, the proof is quite simple. For any h in curly h, we have a unique decomposition, as explained before, in h hat belonging to h, to this space, and h prime belonging to h perp. Then look at this, h of x upper I by the reproducing property is the inner product of h and hi. This inner product, the h prime times hi is 0 because h prime is in the perpendicular space. So this is the same as h hat hi. And again, by the reproducing property, this is h hat of x upper I. Okay? And hence, this function here can be written as by using instead of h hat. Now, since sigma is non-decreasing, the sigma of the norm of h, this here, is less than or equal the sigma of h hat a square plus h prime a square root. Well, this should be h hat, okay? Is less than or equal to this, which is the sigma of h. This is 39. Sorry for that. So the sigma of h hat is less than or equal to the sigma of h. We conclude that L bar of h hat is less than or equal L bar of h because this doesn't move when you replace h by h hat, and this goes down when you go from h to h hat. And this implies immediately the first part of the theorem. And for the second part, notice that if h prime is non-zero, this h prime here, then the L bar of h hat is strictly less than L bar of h because of this, because of the sigma, okay? So h cannot be a solution of the minimum problem unless it coincides with h hat. This is the end of the proof. Now the kernel trick goes as follows. In terms of the expression of h hat like this, a linear combination of hi or of the kappa xi, as you like, for minimizers of 2, we have that h hat of x upper j is this sum here. Lambda I replace the hi by kappa xi of xj, and this is the kernel. So it's a combination of this. Similarly, for h hat, norm of h hat square has this expression, and consequently, solving the minimization problem 2 is equivalent to solving this problem here. It's the minimum with respect to the lambdas of the L of this plus the sigma of the norm, which have these expressions. Well, aside from L and sigma, this problem only involves knowledge of the kernel matrix K, and the solution lambda yields the predictor h bar given by this. Notice that in minimizing this, you don't have to go to the reproducing kernel Hilbert space. You don't have to evaluate inner products in a high-dimensional space. Everything is done in terms of the kernel, at the level of the place the kernel lives. And this is the kernel trick, that you can avoid having to work with the reproducing kernel Hilbert space, which is only has theoretical value. It has allowed us to do all that. all we have done so far. Okay? Let's do an example. I'll do the support vector machine. We did it on 10 October 5, part 2, page 43 and 44. Well, it was an optimization problem of this form. We had to find the minimum with respect to W and B of the norm of W square, subject to these conditions, which were separating points on one side or the other of the hyperplane. Now, the constraints of this problem are the Gj of WB is 1 minus this expression. This should be less than or equal 0. Is this condition here. These conditions are affine in WB, hence are qualified in the sense of the session on October 5. And therefore, there is a unique solution which can be found as an application of the Kernel theorem to the Lagrangian of the problem. The Lagrangian has this term and has one term for each condition. So a Lagrange multiplier and the condition, this condition here. Now, what we found, and it's easy to find on inspection of this, is that the gradient with respect to W is 0. This gives this, that W is a linear combination of the x upper j. Then the gradient with respect to B should be 0, since B only appears as a coefficient of this. You get that the sum of uj y upper j is 0. And finally, we had the slack or complementary conditions, which said that for all j, either uj is 0 or the other condition is 1. This means that if uj is 0, then you are on the limit planes, the margin planes, the margin hyperplanes. Okay, so the conclusion is that the W is a linear combination of the xj, such that the uj is non-zero. They belong to the marginal hyperplanes, this plus minus 1. Remember that yj is plus or minus 1. And these are the support vectors, the ones that data points that are on the marginal planes. These support vectors suffice to construct the maximal margin hyperplane, as we also have for the support vector xk. You can find the b trivially. Now, the duality of this problem is obtained on plugging this expression for the W into the Lagrangian. And you do some algebra, and you find that this Lagrangian is this. Thus, the dual problem, which we know is equivalent to the primal problem, because duality is in force, is this problem here. The upper star is a maximum with respect to u non-negative of this Lagrangian, subject to u non-negative, and subject to this condition obtained from the V. So there is one more condition. Well, now we can go to the soft support vector machine. We didn't do that the last time. There was no time, and actually it is not explained in detail in the slides. So let me do it now, because I think it's very it's a powerful illustration of what has been going on so far. If the data are not linearly separable, as it was for what I have called the support vector machine, what can we do? Well, in this case, we cannot assume that these conditions is valid for all j. There may be j's that violate this condition. Well, if we want to apply optimization tools, a standard procedure is introducing what is called the slack variables, T1, Tn, and consider, instead of these constraints here, as slack constraints. So you allow to violate the minimum one by some amount T of j. The T of j are positive. Okay. In this situation, a convenient function to be minimized is, again, a term with a norm of the W, because this is the part controlling the linear terms. But you want to control also the slack, the total slack, which is the sum of the t's. Now, to balance these two things is always the same game. You take this and sum a suitable constant times this. How to choose lambda is another question, but you choose one, and then this lambda gives a way of balancing these two things. If the slack is very high, if lambda is very high, this will count a lot, and so the minimum will favor this, and the other way around if lambda is small. Okay. So to see at a glance what will be the conclusion, just look at this scheme. Okay. We have, as in the normal support vector machine, we have negative points, which are here are in black. You have positive points, here are in white, and you manage to find a maximum margin hyperplane, which is this represented by this blue line. And then you can have points that do not violate the initial constraints, like all these white points. There are two on the margin line. So these two are support vectors. But there may be some that have a slack, a positive slack, less than the margin. So they are still on the right side of the hyperplane, but they are in the ribbon given by the margins. Well, this is counted as an outlier, and so will be a point like this one here, which is misclassified because the slack variable is too high. So the slack variable moves, this point differs from the marginal hyperplane by too much, by Tj, so much that it goes to the negative hyperplane. And here there is another instance of a little slack that classifies well, but is in the ribbon and not in the right side. Okay. Well, this is explained in this at the bottom, and I repeat that those that are correctly classified are those that are on the right side of the hyperplane and beyond the margin. Otherwise, they are called outliers, and outliers there are of two classes. There are those that are misclassified because they are in the ribbon. They would be perfectly classified because this is plus then, but because this is positive, but they are beyond the margin, so it's an outlier. And of course, the other outliers are the ones that are misclassified, like this one. Okay. Now how are we going to make sure that these assertions are correct? Well, we have the machinery right in place. So the slack or soft, so I'm going to call hard support vector machine, the one explained the day before and reviewed today, and soft or slack support vector machine, the one that has the slack variables. Well, what we have seen is that the soft support vector machine problem is equivalent to this optimization. So we take the function, the objective function, to minimize. The minimization now depends on W on B, which define the hyperplane, and on T, which T1, T1, T2, Tm, which define the slack variables, subject to, well, the slack constraints, which are as for the hard support vector machine, but with the Tj, the Tj's have to be non-negative, and that's it. Okay. Well, there are two sets of Lagrange variables now. They are used for this kind of constraints, and that there will be S1 as M for slack, for these slack variables. Okay. This leads to this to this Lagrangian, everything is fine. The Lagrangian depends on W, V, T, and the Lagrangian parameters U and S. So you have the objective function. I put a negative sign because I want to write this not as one. I want to write this like this minus this minus this, which is greater or equal than 0. So therefore, I put a negative sign in the Lagrange variable. And similarly, for each tj, there is again is a negative. So I put sj here from affecting every tj. Now the solution of the soft support vector machine is given by the following equations, which is just applying the Kernel theorem. Gradient with respect to W of L has to be 0. What do you get? It's like before. You get this expression. This says that W is a linear combination of the data, xj, and the coefficients are these ones. The gradient with respect to B is minus this sum here, and this has to be 0. So therefore, the sum of uj y upper j has to be 0. The gradient with respect to the tj is lambda minus uj minus sj. So this boils down to saying that uj plus sj equals lambda. Then there is the slack conditions. Uj times this condition should be 0, which means that either uj is 0 or this thing is 0 for every j. So either one or the other. And same for the slack variables tj, you either have sj 0 or tj equals 0. This is Kernel theorem. Now, in expression 1 of W as a linear combination of the data, only the terms with uj different from 0 matter. These are the support vectors. And by 4, which is this, these terms satisfy this condition if uj is different from 0. So they are marginal with margin tj, okay? But if tj is 0, then we are okay. The xj lies on the corresponding marginal plane, as in the hard support vector machine. And if tj is bigger than 0, then xj is an outlier, as by definition. They are misclassified somehow. In this case, misclassified or in the ribbon. In this case, 5, this 5 here, says that sj is 0, and by 3, the uj has to be lambda. In other words, the support vector xj is either an outlier, in which case the uj is lambda, or lies on the corresponding marginal hyperplane, as in the case of the hard machine. A final note is that the dual of the soft support vector machine is equivalent to the optimization of this problem. It's just substituting, plugging this expression in the Lagrangian, and you get that the dual of the soft support vector machine is equivalent to the optimization problem, this one, maximizing with respect to u, all this expression, subject to, well, the uj have to be greater or equal than 0, and by the less common, less than or equal lambda. So there are two conditions here. And finally, the linear condition. Well, La proof, as I said, is plugging the expression for W into the Lagrangian together with algebraic manipulations using the other 4 Karius-Kuhn-Tucker equations. And we get the same dual Lagrangian as for the hard case, this one. But in addition to uj bigger than 0, we have this uj less than or equal lambda, I said before. Now, I think that allow me a few minutes, 2 more minutes, and explain the kernel support vector machine, which is, after all, was one of the goals of this session. Since the support vector machine equations, in the support vector machine's equations, the data x upper 1, x upper m only appear in inner products. The kernel trick allows us to replace these inner products by the kernel by any kernel on X. Now, not necessarily of vector type. Now or before, need not be of vector type. For example, the kernel version of the dual soft support vector machine that we just saw is just doing the replacement where you had a dot, you get a kernel, but otherwise it's just the same. This maximization occurs in the space X, not in the feature space. Okay. Okay. Implicitly, is running the algorithm in the feature space, but without having to worry about operations in the feature space, which might be very costly because of very high dimension. Well, this algorithm delivers a hyperplane separator in the feature space, which in the original set X becomes a highly nonlinear decision rule or decision boundary. The kernel trick guarantees that no operations are performed in the feature space, but only in the original set. Well, this remark, I already said it before, but let me stress it. The analysis of the support vector machines presented above, of soft support vector machines, has not applied the kernel trick theorem, representative theorem, to derive that the predictors are linear combinations of the functions kappa of xj, x, nor to establish the optimization problem by which they are governed. Instead, we have followed the explicit path offered by the Cartridge-Tucker theory. But we could, of course, follow the first approach, of course. In the case of the select support vector machine, for example, the sigma in the representative theorem would be sigma of t equals 1/2 of t squared, which is strictly increasing for t greater or equal than 0. And so the sigma of h, or norm of h, would be 1/2 of the norm of h squared, which is the usual one in that setting. On the other hand, the function, this function in this case would be the maximum of 0 and 1 minus y upper j, h of x upper j, which is the Hinge laws. It is called the Hinge laws. For details, including sharp restrictions of the algorithmic computations, see the book by Shalef Barnes and David, and many other books. So this is just the beginning of the study of kernels, and this is as far as I could go. And next time, I think that here you have, I'm not going to do this, kernel methods for pattern analysis. You have ways to keep studying or working on being inspired by these things about kernels. And also this historical paper is very nice, The Journey of Graph Kernels Through 2 Decades, Graph Kernels, okay? And finally, I don't have time today. Well, Google is wrongly written, okay? The computations we are trying to do, I'm going to use the collab environment of Google, okay? This is something I am doing in collaboration with Eduardo Ulises Moya. This is work in progress. Eduardo Ulises Moya is in Mexico, in Jalisco. He is running the Artificial Intelligence Center there. And we have so far notebooks in the collab format for principal component analysis that I mentioned the first Tuesday, for linear regression, for polynomial regression, and one example of kernel learning. But it's too late, so I will take some time tomorrow to explain at least one of these. Thank you very much for your attention. And let's see if there are any.
I have one question.
Yes.
So with these kernel methods, you could potentially model any nonlinear function, right?
Well, I wouldn't say this in this way. You can model many nonlinear functions, but whether you could model any, I think at this moment, I don't think so, okay? Because it all depends on the feature maps, okay? And the feature maps have to be in such a way that they have the reproducing property, okay? So you cannot manage arbitrarily nonlinear maps in the kernel. Well, this, in part, kernel methods are in use. They are important. Importance has not decreased in time, even with deep learning, deep neural networks. But of course, they lack some of the capabilities that deep neural networks have, and that we are going to explore in successive sessions. Okay.
So following on this answer, the expressivity of these methods is measured in the feature space.
Well, in the kernel you choose to represent your, let's say, similarity. Suppose you had the DNA strings, okay? And that you'd like to apply kernel methods to these DNA strings. Then you would have to find a similarity measure between these strings. And this is done. This, in the references I gave, I am giving it in the last slide. You can find that, okay? Once you have this similarity measure, then you can put the machinery to work by figuring out what is the feature map and so on. And using the trick, the kernel trick, you don't have to worry about actually what is the feature space. Okay? This is the way it goes.
But
again,
then you need some inductive bias in your modeling.
I think that the inductive bias is done in the way you choose the kernel. Is more or less the analogous of the inductive bias is choosing the kernel, okay? Which is the similarity and what do you expect of it. Now, the place where you can work on that, of course, is in figuring out what kernel do you need, and then the next thing to leverage is the algorithms. At the end, what algorithms do you apply to the matrix, to the gram matrix, to figure out the best prediction? Okay, and they are two roughly independent things: the algorithms and the kernel. Okay. Thank you to you. We just have seen that for the case of the soft support vector machines, it works very finely. Okay. Now let's see if there is. I don't know if there are other. No, there are no more questions, I think. So thank you very much. We meet again tomorrow at 4 in the afternoon. And tomorrow the lecture is about roughly the stochastic gradient descent, which is the power course of much of deep learning, okay? The optimization of much of the machine learning, of deep machine learning, okay? So bye-bye.